Hey guys, welcome back. It's been a little bit. We are back for another riveting edition of Let's Try This Flipped Classroom thing. Today we're starting chapter 9 and we're looking at properties of radicals today. So just to kind of start off, our essential question is how can you multiply and divide square roots? Okay, so that's our big main concept for this specific unit or this specific lesson. So make sure that you get that essential question written down. When I look, we've got quite a few vocab words, so I'm gonna kind of push my way through these, I guess you could say, just so that we definitely have enough time and I'm not going over on some of this stuff. So a radical expression is just an expression that contains a radical. Remember, a radical is just anything that's got a square root sign. The second one, which is a really, really big topic for us when dealing with radicals, is rationalizing the denominator. So one of the big things in math is that whenever you have a fraction of any sort, you cannot have a root sign in the denominator. So we have this process that's called rationalizing the denominator. And here's the definition of it. To eliminate a radical from the denominator of a fraction by multiplying by an appropriate form of 1. Okay, and the definition doesn't make a whole lot of sense right now, but it will once we do the process, and that's kind of one of the last parts of the video that I'm going to talk about for today. Then we have the conjugate. The conjugate is basically just the opposite. So when we have a type of expression, we'll say, that has like the number a times the square root of b and then plus c times the square root of d, the conjugate of that binomial would just be the exact same expression, except it's got a subtraction sign to it. Okay, and that's just conjugate. That's another fancy way of saying opposite, basically. So it's the same numbers, same order, it's just got a different sign. Like radicals are just radicals with the same index and radicand. Okay, so like here would be an example. Remember, the index is the number that goes, that's the root that you're taking. So let's say we have the cubed root of 20, and then you want to do like 5, and then cubed root of 20. So the index, these little guys right here, what's inside, have to be the same. And then the radicand is the number that's underneath the square root sign. Okay, so then in this instance, we would have 6 cubed roots of 20. So that's just a super, super quick example. We'll do more of those. Probably not in this video, but for the next video. The simplest form of a radical. Okay, so first off, here's its definition. It's an expression involving a radical that has an index and it needs to meet 3 conditions. Okay, so that's a key point. There are 3 conditions that this needs to meet in order for a radical to be in simplest form. First off, no radicands have perfect nth powers as factors other than 1. Okay, basically, you have to take everything out before you say that it's your final answer. Here's a good example of this. The square root of 20, that's not simplified. Remember, there's a perfect square inside of that. The perfect square of 4 and the perfect square of 5, or 5 is not a perfect square, but 4 is a perfect square. Okay, this is what they're talking about here. Okay, there cannot be a perfect square or a perfect cube or a perfect fourth inside of whatever type of index you're trying to find. Number 2, they cannot have fractions. And then lastly, number 3, no radicals appear in the denominator of the fraction, hence as to why we have the rationalizing the denominator, the orange definition. okay? So that's like law, okay? You got to make sure that in order for it to be in simplest form, it needs to meet 1, 2, all 3 of these requirements, okay? So make sure you get this stuff written down. If you need to, pause the video, totally okay. Take your time, whatever you need to do. So what I've done next is I've just put 2 core concepts. Your book separates them and has you do like an example or 2 of one and an example or 2 of the other. I'm just going to put both of them together, and then I'm going to talk about both examples just to kind of speed up the process a little bit. Okay? So first off, the product property of square roots. Basically saying the square root of a product equals the product of the square roots of the factors. Okay? Basically saying like, so here's kind of, if I take this algebra or this number piece back just one more step, let's say we have the square root of 45. What the product property of square roots is saying is that you have the right as a mathematician to break this up into 2 separate, into a perfect square and a non-perfect square. So then what you would be able to do is you would be able to say that this turns into 3 root 5. You can check this. You can check to make sure that you have simplified this radical correctly. Take the square root of 45 in your calculator. Hopefully you've got your calculator handy. If you take the square root of 45 in your calculator, that gives you approximately 6.71. Okay, and I know that it's a longer decimal than that, but I'm just going to round. Now, in my calculator, if I take 3 root 5, I get the exact same approximation, 6.71 approximately, and the decimal ends up being the exact same. But that's all the product property of square root says, is that you can take a root and simplify it. You have the right to do that as a mathematician. Okay? But the other key characteristic of this is you need to make sure that the number that's left needs to be greater than 0. And then the quotient property of square roots. Whoopsies. Sorry, guys. The quotient property of square roots. Remember, quotient just means to divide. Basically, they're saying if you have the square root of a quotient equals the quotient of the square roots of the numerator and denominator. Okay, great. Basically, you have the right to take this entire square root, like this big guy here, break it up into 2 separate roots. Because taking the square root of 3/4 or of 0.75, that's not going to give you anything like super easy to deal with. But we know that 4 is a perfect square, so we can break this down so that we can at least have the denominator rationalized, so that we can follow those rules. Remember on the last slide, one of the key characteristics that it needs to meet is that this down here cannot have a square root in it. Okay, so I know I just have done a bunch of talking and kind of want to just get to the couple of examples, but one thing that I really, really encourage you to do, you guys, you've got 4 examples on the next slide, or right below, excuse me. Please, please, please go ahead and, for your sanity, I promise you this, I want you to write down the first 10 perfect square numbers. 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. And the next thing I want you to write down, so again, that's 1 squared, 2 squared, yada, 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 3, 4, 5, 6, 7, 8, 9. So that's the first 10 perfect square numbers. Then I want you to go ahead and find the first 6. So 1, 2, 3, 4, 5, 6 perfect cubes. Okay? So if you don't have your calculator, you need your calculator for these examples. So 1 cubed is just 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, and 6 cubed is 216. Having these numbers at your disposal is really going to help these next couple of examples go quicker. Okay, so right on the left-hand side where it says questions, right underneath there, write these two lists. Okay, or somewhere where you can have these two lists super, super handy. Okay, so you guys, here's why I think that those two lists are really, really important. We're basically going to do a few examples where we're trying to simplify, right? The directions say to simplify the expression. So the first thing you're going to want to go through and do is figure out, how can I break 108 down? Is there a perfect square inside of 108? And as you guys can see, there is a perfect square inside of 108. And it might take a little bit of work. Okay, I know that you guys don't have all of these steps listed for you, but you might have to go through and you might have to figure out, okay, 108 divided by 4. Okay, that gives me 27. I can take that a little bit further. 108 divided by 9. That gives you 12. There's still a perfect square inside of 12, so let's try a bigger number. 108 divided by 16. Okay, that's not a perfect square, so that's not going to work. 25 is not going to work because it's not a multiple of 5. But if I take 108 divided by 36, that gives me, like 36 is a perfect square. So we can break this down into the square root of 36 and the square root of 3. Why is this not coming? Why is this not working? Okay, so we can break this down. Okay, whatever. We'll just do this.